The third chapter of the syllabus is coordinate geometry. What is coordinate geometry? Coordinate geometry is about dealing with different points on the graph and then its respective graphs taken further in the syllabus. Let's see in brief what coordinate geometry is. But before we discuss about the mathematical concept of understanding coordinate geometry, let's apply a real-life situation in understanding coordinate geometry more better. Connecting with real life to understand coordinate geometry more better. So coming to the introduction, what was the need for the mathematicians to come into researching on the existence of coordinate geometry? Or what was the need for introducing coordinate geometry into the branch of mathematics is the biggest question which need to be opened through this opening problem. So let's see the real life situation. For example, I assume this to be a sea. I have the sea, the whole of the sea, in which there's a ship which is sailing by out here. So here is the ship which is sailing by, and the person inside the ship would like to reach to the bank in the nearest position. So his destination to reach to the bank, which is out here, would be just based on coordinate geometry. Interestingly, this is a real life situation which demands for coordinate geometry. So let's see how he estimates the bank through application of coordinate geometry. The ship out here in the sea is assumed to be 2 units, 1, 2, and 3 units. A person standing here would like to see the distance moving 2 units towards this side, and then exactly when the ship moves to this place, then from here the ship needs to move 1 unit down, is how we understand the distance being measured. So the person who is 2 units left and 1 unit down is where he reaches the bank in the destination. So let's see how this is possible more briefly through the graph. So I assume a graph. I assume x and y axis intersecting at origin, and I assume the ship is at the origin initially in the sea, assumed in the sea. Now his destination to reach at point P is identified through coordinate geometry. A person standing here in the ship in the sea would move 2 units, 1 and 2, 1 and 2 units to the left, and then he would move 1 unit down. Is how we understand the opening problem. So a ship which moves 2 units left and 1 unit down, or 1 unit towards south, where we take the direction as east, west, north, south. So I assume through direction that this ship is moving 2 units towards west and 1 unit towards south. Then he reaches the destination of the bank, indicates on the graph that he is moving 2 units to the left of x-axis and then 1 unit down of y-axis, and then he reaches the destination P. So how do we define P in the graph is the biggest question which connects coordinate geometry with real life situation like this. So when I see the ship moving 2 units left, I see that he is moving negative 2 units to the left, and then when the ship moves 1 unit to the south, I see that the ship moves 1 unit towards P. So I locate this point P with x moving 2 units minus 2 units, that is to the left, and then the point P which moves 1 unit down, and therefore this would be -1 and this would be minus 2, because the negative values come on the negative side of x-axis. On the left we have negative x values, on the right we have negative y values, and therefore we have the coordinates of P which come out to be minus 2, minus 1. The ship destination to reach to the bank is when it moves to the point minus 2, minus 1, assumed through origin. Is how we connect the real life situation of a ship in the sea to reach to its destination in the bank. There are many such examples other than this through which we understand coordinate geometry more better. An aeroplane moving out with certain distance would reach the airport only by using coordinate geometry. A pilot cannot estimate the airport for landing down without estimation through the perfect coordinate geometry. Is how we apply through real life applications. Many more examples to follow with. Before we enter into understanding coordinate geometry more stronger, let's try to understand the structure of the Cartesian system. What is Cartesian system? A Cartesian system through which we understand the location of points and the graphs and the various other aspects related to the graphs and the points. So let's see in brief how the Cartesian system plays a significant role in the coordinate system or the topic of coordinate geometry. Let's see the Cartesian system. What is Cartesian system? Cartesian system deals with the two lines initially being perpendicular. First, I have two lines which are assumed to be perpendicular to each other, cutting at 90. And I take the horizontal line denoted by x, or this is called x-axis, and the vertical line assumed to be called y, or the y-axis. So the horizontal line in the Cartesian system is referred as x-axis, and the vertical line in the coordinate system is referred as y-axis. It's a rule of the coordinate system. They intersect at one point, and the two lines perpendicular and intersecting at point is referred as origin, generally denoted by this, and this is referred as origin, because it is from where we try to take all the different situations, just like in the ship in the previous example problem, where the ship was assumed to be on the fixed base, that is origin. From where we can identify the comparison of origin with the rest of the points. So the intersection of the vertical axis and the horizontal axis is called the origin. The horizontal axis being called x-axis and the vertical axis being called y-axis, and the point of intersection of those two axes being called origin is the rule of the coordinate system. Let's continue further. Here comes now understanding on what would be the definition for the right side of the origin, and what would be the definition on the left side of origin, and what would be the definition up the origin and down the origin. So each of the four directions have their own definitions as a rule of the coordinate or the Cartesian system. Therefore, I have to define the right side of x-axis, which is positive x-axis. Like I take all the values on the right, which are denoted by 1, 2, 3, 4, 5, 6, and 7, etc. It goes on and on till infinity. And the left side of x-axis is denoted by negative values, negative real numbers like minus 1, minus 2, minus 3, minus 4, minus 5, so on and so forth. Similarly, all the values on the positive side of y-axis are defined as 1, 2, 3, 4, 5, etc. And this is called minus 1, minus 2, minus 3, minus 4, minus 5, etc. Therefore, I have all the values coming on the right as positive x values, negative x values, positive y values and negative y values. Also importantly, it is very important to note that if I refer to this value 3, it indicates my x is 3 at this position. It's nowhere related to y. When I take, say, this value, then I say this point refers to y equals to -4, but this is nowhere related to x. It is independent of x. So this relates to y and this relates to x, is how we understand the values of x on x-axis and the values of y on y-axis. Also, we note that all the numbers on the x-axis on the right side of the x-axis are positive real numbers, and all the values on the left side of the origin on the horizontal axis are all negative real numbers, with origin being the fixed point of intersection of both the axes. Similarly, all the values on y-axis are also the set of positive real numbers, and all the values on the down of y-axis are also set of real numbers which are negative. Positive real numbers, negative real numbers, positive real numbers and negative real numbers is how we understand the coordinate system, the Cartesian system connected with x and y-axis. Origin, x-axis, y-axis are the base rules of the Cartesian system. Now that we have discussed about the Cartesian system, let's try to continue further with the properties and the rules of the Cartesian system. So every point represented on the Cartesian system has its own rules and the respective understanding. So let's see the different rules applied in the Cartesian system. The first of that being the quadrant rule. The quadrant rule plays a vital role in understanding the Cartesian system subdivided into 4 parts. So let's see how the quadrants gets connected with the Cartesian system in its own respective rules. Quadrants. Let's revisit the Cartesian system of the horizontal axis, which is x-axis, and the vertical axis, which is y-axis, back again from the previous session. As I take my x and y axis, x dash is my x-axis and my y dash is my y-axis, which intersects at origin, and all the positive side has positive x values, and here negative x values, positive y values and positive negative y values. So my first positive x-axis has all the values coming out from positive real numbers. My negative x-axis has is how I get all the values filled up. Now let's see what each of the rules says. I always start from right to the left, that is going in the anti-clockwise direction of the positive x-axis. So I start from here and I go in this direction, then I go in this direction, then I go in this, and then towards this. So I see that when I proceed in the anti-clockwise direction, the whole of the vertical and horizontal axis which are seen out here is dividing the whole of the board. For example, I take this board, these two axes are dividing the board into 4 parts. 1, 2, 3, 4 is how I divide the plane into 4 parts. So here I have the plane the marker board, which is divided into 4 parts, part 1, part 2, part 3, part 4, going in the anti-clockwise direction. So each of the region has its own independent properties. Now Cartesian system rule says that we divide the Cartesian plane or the coordinate system plane, the board, into 4 parts, and each of the part plays a vital role in the topic of coordinate geometry. So this is referred to as first quadrant, and this is referred to as the second quadrant, and this is referred to as the third quadrant, and this is referred to as the fourth quadrant. So there are totally 4 quadrants which the whole plane is subdivided into by the 2 perpendicular lines, x-axis and y-axis. So using this, let's see what each of the quadrant has to play its role in the coordinate system. Now coming to first quadrant, what is its role in the coordinate system or the topic of coordinate geometry? Let's see each of them. When I see the first quadrant, I always see that this is the region which refers to positive x values and positive y values. So I have this x value is positive, usually the point which refers to the x value is positive and the y value is also positive in this region. Secondly, when I go to the second quadrant from the anti-clockwise direction, I clearly see that in this region I have x values which are negative and my y values which are positive. Therefore, my second quadrant, x is negative and y is positive. It's very simple. Similarly, when I go through the third quadrant down here, I see that my x values are negative and my y values are also equally negative as seen in this diagram. So I refer to x being negative and my y equally being negative in the third quadrant. And the last quadrant which lies out here is the fourth quadrant, and in this quadrant clearly when I see through the diagram, I see that my x values are positive and my y values are negative. Therefore, my x is positive and my y is negative. So finally, we see that when I see through each of the quadrants, the region in which x is positive and y is positive is called the first quadrant. And the region in which x is negative and y is positive is called the second quadrant. And the region which refers to x negative and y negative, that region is called the third quadrant. The region in which x is positive and y is negative is called the fourth quadrant in the branch of coordinate geometry, in the coordinate system rules and regulations. Now that we have discussed about quadrants, the 4 types of quadrants in the coordinate system or the Cartesian system, let's see how we can just use its significance in real life. But before that, it's very important to identify that how we locate the point in the quadrants is what is the biggest question in coordinate geometry. So before we understand the real life situation, let's get into the coordinate system in which the points are located. So quadrant and the rules of locating of a point is what is the session for today. Locating a point using quadrants is what we deal with once the topic of quadrants is learnt. So now that we know the rules of each of the quadrants, quadrant 1, quadrant 2, quadrant 3 and quadrant 4, Next comes on how we can locate through their own respective definitions. So let's revisit the quadrants which we have learned in the previous session to understand the locating of a point. So let's see how we can locate a point. Now when it comes to x and y axis, and this, now let's try to locate some points on x and y axis positively, negatively on either sides of the origin. So here I have the positive x values as discussed, and let's locate them with 0, 1, 2, 3, 4, 5, 6 and so on and so forth. Negative 1, negative 2, negative 3 and etc. Here lies 1, 2, 3, 4, 5, minus 1, minus 2, minus 4, minus 5, etc. So I have each of the x values on x and y axis as we have already discussed in the previous session. Now let's see how we can locate a point in the respective quadrants. As we have discussed, the first quadrant denoted by Q1 lies in this region, and the second quadrant denoted by Q2 lies in this region, and the third quadrant denoted by Q3 lies in this region, and the fourth quadrant denoted by Q4 lies in this region. So each of the denotions of Q1, Q2, Q3 and Q4, let's see how we can locate a point in its respective quadrant. So for example, I have the point generally denoted by x, y. So before we enter into locating a point, let's recap on how the notation is done for a point. What is the rule for locating or denoting a point with the symbols? So when I take the point P, generally I denote with the open brackets with x, y, where x refers to the first value or the x coordinate, that is a value on the x-axis, and y refers to the y coordinate or the value on y-axis. So here I have this value which lies on x-axis, and here I have the value which lies on y-axis. Is how the rule is applied for the point. The point generally denoted by x, y. So for example, I have the point as minus 3, 2. For example, I take P as minus 3, 2. Then this clearly indicates that this is the x coordinate and this is the y coordinate. So for example problem, minus 3 is the x coordinate and 2 is the y coordinate. And minus 3, so x coordinate here is minus 3 and the y coordinate here is 2. Therefore, my x coordinate is minus 3 and my y coordinate is 2. As we know that the x coordinate is negative in this example problem, clearly I understand that it being negative, x value lies on the left of the origin. So I have the x coordinate. Usually each of this represents 1 unit. Each of the distance represents 1 unit, and therefore I break every x-axis into 1 unit subdivided part, and equally the y unit also is divided into 1 unit subdivided part, which indicates that minus 3 refers to the minus 3 units on the left side. The negative sign indicates on the left. So with the x values being on the negative side, I have 1, 2, 3. I move 3 units to the left, and therefore my point P is said to be initially with x value out here, and then my y coordinate being equal to 2 indicates that this is the positive y value, which clearly can be identified in this quadrant as the positive y value, which is 2 units up. So I move 2 units up, but I don't move from origin, because first it moves through x-axis and then it moves through y-axis. So a point P moves first 3 units left and then moves 2 units up. This is where finally the point P moves. So when I locate the point minus 3, 2, I understand that it moves 3 units left and 2 units up. And finally, I see that this point P is now in the second quadrant. So the point P, which is minus 3, 2, lies in the second quadrant, is how we locate the point in each of the quadrants using the definition of quadrant concept. Quadrants and locating a point are very much connected through this example problem. Now let's take another example problem to understand the concept more stronger. Let's take an example in which my question says, locate the position of the point A equals two comma minus 5 by 2 in the Cartesian system. So my question out here is, locate the position of the point 2 comma minus 5 by 2 in the Cartesian system. So let's see how we can locate the point using the rules of the Cartesian system. The first thing what I do before I locate the point is, of course, construct the Cartesian system, the base for locating the point, the base for identifying its quadrants. So let's construct the Cartesian system. Intersection of horizontal axis and vertical axis is what is called Cartesian system. Intersects at origin, this is x-axis and this is y-axis. And then let me take some points out here. I have the negative y values. In this manner. Now comes the question on how to locate the point. So let's get back to the point A, which is given to be 2 and minus 5 by 2. As clearly seen that this region is called the quadrant number 1 and this region is called the quadrant number 2. And this region is called quadrant 3 and this region is called quadrant 4 in the anti-clockwise direction, Q1, Q2, Q3 and Q4. Now with this, we also know that the first value of the given point refers to x coordinate and the second value refers to the y coordinate. So here my x coordinate is 2 and my y coordinate is minus 5 by 2, which is in decimal form as negative 2.5. Converting to the decimal form, minus 2.5 is my y coordinate, 2 is my x coordinate. Now comes in locating this point in the Cartesian system. So as I see here, I see that this point is x coordinate, which is positive, and this is 2 units, which makes me understand that the origin moves 2 units to the right initially, and then it moves towards y coordinate with a distance of negative 2.5 units. So here I have this point which moves 1, 2, 2.5. So I exactly have this point moving negative 2.5. Oh, this would be in the down. So I have this to be moving 1, 2, 2.5. So I have this exactly moving at negative 2.5. Therefore, I have my point which is now located at this. My point A is out here, which is 2 comma minus 5 by 2 or minus 2.5. So the point A is identified in the Cartesian system to be in the 4th quadrant. Using the rules of the Cartesian system, we can locate any point. This point being in the 4th quadrant. Any point in xy coordinate system can be located using the rules of the Cartesian system. Next, now that we have discussed about locating of a point in the Cartesian system with respect to its quadrants, let's see an exceptional case of an origin. Origin is also referred as a point, but which quadrant does origin lie is the biggest question. So let's try to take in brief the origin, locating the origin in the Cartesian system. As we know that origin is the point of intersection of the horizontal and the vertical axis. I have this axis as xx dash and yy dash, which intersect at this point, and this is the point which refers to origin, denoted by O. So generally, the coordinates for origin are also equally important because this point also lies in the Cartesian system. It lies in the plane at some position. So what are its coordinates? What is its x coordinate and what is its y coordinate is the biggest question in the branch of Cartesian system. So what is origin? Origin in general English context dictionary refers to the source or the root cause of the source. So here we define origin as the root cause of defining all the points in the marker board or in this plane. So the source of or the root cause of defining all the points is origin, and therefore we refer to this as the initial point. So origin is referred as the initial point of Cartesian system. Now, because it is initial point of Cartesian system, it is understood to have been without moving any units right or left or up and down. It is initially at the point where the x coordinate is assumed to be 0 and the y coordinate also is assumed to be 0. Is how we understand the origin as connected with the Cartesian system. Origin in the branch of mathematics is the root cause, the initial point in the Cartesian system, and its coordinates are 0, 0. We denote origin by capital O and its coordinates being 0, 0 is how we define origin in the branch of mathematics. Now the question comes, where does origin lie? Which quadrant does origin lie is the biggest question out here. So as we see here, we have the first quadrant out here. As discussed in previous sessions, I have the quadrant 2, which is here, the quadrant 3 and the quadrant 4, which lie in each of the regions Q1, Q2, Q3 and Q4. Now comes the biggest question on which quadrant is origin. Which quadrant does origin lie? So here comes the question. As we see that it is in its initial position, it is said to have been neither in this region, nor in this region, nor in this, nor in this. Equally, we sometimes assume that origin lies in all the 4 quadrants, or sometimes we say origin doesn't lie in any of the quadrants. So because it is an initial position, we don't count the origin in any of the 4 regions as subdivided out here. Therefore, it's a very important note that origin being the initial point doesn't lie in any of the 4 quadrants Q1, Q2, Q3 and Q4. So here it refers that origin being the initial point doesn't lie in any of the 4 quadrants. It is independent of the 4 quadrants but plays a vital role in the Cartesian system, connected with all the 4 quadrants Q1, Q2, Q3 and Q4. Origin capital O 0, 0 are its coordinates. Now that we have discussed about even the special case of an origin, let's also realize the different types of terminologies used for the x and y coordinates of a point. So as we have discussed about a point in the Cartesian plane, we have discussed about a point P generally being denoted by x, y. Is how we denote for P being x, y. And x refers to the x coordinate, which is also called with the other name called abscissa. X coordinate of the given point is called abscissa and the y coordinate of the given point is called ordinate. Is how the different types of terminologies are used in mathematics to define the point. X coordinate refers abscissa and y coordinate refers to ordinate. So when we take with a recap of the coordinate system, we understand that x dash and y dash taken in the Cartesian plane with origin being the intersection point of the lines. Then it refers that in the first quadrant the abscissa is positive and the ordinate is positive. And in second quadrant the abscissa is negative and the ordinate is positive. In the third quadrant the abscissa is negative and even ordinate, the abscissa being negative and even the ordinate being negative. In the fourth quadrant, abscissa is positive and the ordinate is negative. Is how I understand the abscissa and the ordinates which define the coordinate system with the respective signs. Plus plus for Q1, minus plus for Q2, minus minus for Q3 and plus minus for Q4. Is how we understand the different terminologies referred to x coordinate called abscissa and the y coordinate called the ordinate. So for example, if I take the point P as 2, minus 3 implies my abscissa as 2, that is my x coordinate is 2 and my ordinate is minus 3, that is my y coordinate is minus 3. And overall my point, locating of a point says that my point moves 2 units to the right and minus 3 units down. So this point moves 2 units to the right and 3 units down, and here I have the point minus 3 and here it is 2 and here is the point minus 2, minus 3. The point is now located in the fourth quadrant using the signs of the abscissa and the ordinate. Locating a point through abscissa and ordinate. through an example 2, minus 3. Now that we have discussed about locating a point in various regions of the quadrant 1, quadrant 2, quadrant 3 and quadrant 4, now comes on what would be the position if I would like to locate a point on the horizontal axis or the vertical axis itself. So today's session is about locating a point on the horizontal axis initially. Locating a point on x-axis, the horizontal axis. So let's recap with the Cartesian plane. Now with the introducing of the Cartesian plane, x dash and y dash, with origin being the intersection, let me just take 1, 2, 3, 4, minus 1, Now I have these points located out here in the Cartesian plane. Now I wanted to locate a point exactly out here. Here lies Q1, here lies Q2, here lies Q3 and here lies Q4. Now here the question is to locate a point P at this region. So how do I locate this point P exactly in between? So I understand that this point is clearly around 2 units from 2.5 units from origin. So I have this to be this resistance being 2.5 units to the right. And now after moving 2.5 units to the right, it doesn't move up or down. That means there's no change in the y coordinate. It is 0 itself from the initial position. So my initial point, which is moving 2.5 units to the right, makes me understand that my point P moves 2.5 units to the right and doesn't move anywhere down. So I have my 2.5 which comes out here as 2.5, 0. So the point which moves towards right on x-axis is 2.5, 0. So I could identify the coordinates of P as 2.5, 0. Let's take another point as a review exercise. For example, I take this point minus 3 and let's see the point minus 3 on x-axis. How do we locate this point and what are its respective coordinates? I clearly see that this point minus 3 is minus 3 units or 3 units to the left, and therefore this has, say, the point Q out here is nothing but minus 3, 0, because this moves along x-axis but there's no change up and down. So this doesn't have its y affected as in the previous case. Only the x coordinate gets affected. Therefore, for point Q, the abscissa is minus 3 and the ordinate is 0. So what do we understand from seeing these two coordinates? What is the learning outcome? Clearly, we see that if we just try with another coordinate, say, let me take out here as R, then clearly I see that the coordinates of R are 1 unit to the right, no change in y. Therefore, 1 unit to the right, so plus, and then no change in y is what we observe. So what do we observe as the learning outcome in all these 3 coordinates is the biggest question out here. When we investigate the points P, Q and R on x-axis, we see that the point P is 2.5, 0, point Q is minus 3, 0 and point R is 1, 0. We clearly see that each of the points have their y coordinates as 0, because any point on x-axis, there's no change in y, but there's a change in x. So any point on x-axis, there is a change in x, but there's no change in y. Therefore, my note is every ordinate of a point on x-axis is always zero. So this is the learning outcome in case of any point on x-axis. Every ordinate or every y coordinate of a point on x-axis is 0. So any general point you take on x-axis would be in the form x, 0 for all x belonging to the real numbers on x-axis is what we learn as the learning outcome. Any point on x-axis is in the form x, 0. Now that we have discussed about locating a point on x-axis, the next question comes on what is the position when I locate the point on y-axis. When I locate the point on y-axis, let's see the investigation on how its coordinates change respectively, as in the case of x-axis. So let's revisit the Cartesian plane. Imagine the Cartesian plane x, x dash, and y, y dash. With each of the points taken in this form. Now with this coordinate system, let's see any point I pick on the y-axis. Say for example, I have this point P located at this position at 4. So let's see what would be the coordinates of this point P located at 4. Clearly, when I see this point P along x-axis, I see that this point starting from its initial position does not change along x-axis. It directly jumps up 4 units towards y-axis. So this clearly makes me understand that there's no change in x, but there is a change with a jump of 4 units up in y-axis. Therefore, I see that the coordinates of P, which jump 4 units to the top with no change in x, clearly makes me understand that its x coordinate does not change, so its initial point, which is 0, remains the same. It's only its y coordinate being changed jumps 4 units up to the positive side, and hence it affects with 4 units out there. Is how we understand the coordinates of P being 0, 4 out here. Let's try with another example. So for example, I have a point out here which is denoted by Q. Let's see the coordinates of Q. Now as I see the coordinates of Q, as in the case of P, clearly I see that Q jumps 2 units down, and therefore without affecting the value of x remaining 0, the y gets affected by moving 2 units down to the negative side, and hence my Q is this. Let's investigate with one more example. Say I take this to be R. Let's see the coordinates of R. My R coordinates does not affect with x, as in the case of P and Q, and hence x remains same, and then my y coordinate jumps 5 units to the top, so the positive 5 comes into the y coordinate. is how I get the abscissa and the ordinate for each of the points P, Q and R. Now comes the question, what is the outcome of this investigation? As clearly we see that in each of the outcome, the x coordinate is 0 and the y coordinates change accordingly with the position or the locating of the point. So each of the x coordinates being 0 implies that for every point on y axis, the abscissa will be 0, unlike the x axis. So here I note every abscissa on the y axis is equal to 0 is how I make the outcome. Every abscissa on the y axis must be 0. Just like for x axis, every ordinate on the x axis is 0 and every abscissa on the y axis must be 0. It cannot change because any point on y axis changes doesn't affect the change in y. Any point moving along x axis doesn't change the effect of y, and hence for x axis y coordinate is 0 and for y axis x coordinate is 0 is how we understand through the applications. An example problem connected with the points on y axis and x axis. Now that we have discussed about coordinates in the Cartesian plane with each of abscissa and ordinate defined on each of the location of the position on x-axis, y-axis, origin or in any of the 4 quadrants, now comes in applying the situation in real life. So let's see how we can apply the coordinate system or locating of a point in real life using the concepts we have learnt. Let's take an interesting real life problem. For example, my question here says, locate the possible positions of horse in the game of chessboard. So here my question is about locating the possible positions of horse. The horse in the chess game is applied through the rules of the game. So we all know how the horse moves in the chessboard. So my question out here is to locate the possible positions of horse in the game of chessboard. So let's see how we can locate the various positions as assumed with the horse on the origin. So let's try to use this in real life connected with Cartesian plane system. So let's see how we can locate through the graphical XY coordinate system. Assuming this plane to be the chessboard, this being the center of the chessboard, and let's assume that the horse is out here. Let me assume that the horse is out here. Now here, let's take the values on x-axis as 1, 2, 3, 4, etc. And here comes -1, -2, etc. So with this coordinate system, now comes the assumption that the horse is assumed to be in its initial position, that is at origin. So with the horse being on the initial position, I had to locate the possible positions of horse in the game of chessboard. Before we enter into solving this problem, let's try to understand the rule of the horse in the chessboard. We know that a horse in the chessboard moves with the rule 2 units right or 2 units left or 2 units down or 2 units up, and then moves 1 unit next. So if the horse moves 2 units right, it can either move 1 unit up or it can move 1 unit down, is how we locate. If the horse moves 2 units left, then the horse can either move 1 unit up or it can move 1 unit down. If the horse moves 2 units up, it can move either 1 unit right or 1 unit left. If the horse moves 2 units down, it can move 1 unit left or 1 unit right, is how we understand the different positions of horse. So with this, let's see how we can apply this in the situation. So initially I have the horse moving 2 units to the right and 1 unit up. So my first position out here is this P, which is located here. So my position P initially is when the horse moves 2 units right and 1 unit up, and therefore my coordinates would be positive side of 2 and positive side of y. So this is one of the coordinate which I identify of the movement of horse. Similarly, the horse can also move 2 units right and 1 unit down, and therefore I have the second chances of P1, the P2 being it moves 2 units to the right and 1 unit down, and therefore this moves positively 2 units right but negative 1. Because it moves 1 unit down, it moves to the negative side of y-axis, and hence coordinates are this. Similarly, my P3 is when the horse moves 2 units left and 1 unit up. The horse moves 2 units left and 1 unit up, and this comes out to be -2 and 1. Coming to P4, the horse moves 2 units left and then 1 unit down. So it moves 1 unit down, and I get this to be -2, -1. Similarly, I have the 4 other cases where the horse moves 2 units up and 1 unit right. So I have this P5 which locates to moving 2 units up and 1 unit right. So let's see how the coordinates move along these 2 cases. Now that these 2 cases are given by these 4 coordinates, these 2 cases are given by the next 4 coordinates. Continued. Now here we have the vertically moving position of the horses, where my P5 is when the horse moves 1 unit right and 2 units up. So the horse moves 1 unit right and 2 units up, and then I get this to be the coordinates 1, 2. Similarly, my next coordinate is when the horse moves 1 unit right and 2 units down. So I have my coordinates which are given by 1 unit right and 2 units down, and hence -2. Next, I have my P7, which is when the horse moves 1 unit right, 1 unit left, and 2 units up. So here I have my coordinates which refer to 1 unit left and hence -1, and 2 units up, so +2. Similarly, the last case being that the horse can move with 1 unit left and 2 units down, and therefore it moves both the ways -1 and -2. Moving to the left -1, moving down it's -2. So these are the 4 possible coordinates which I identify through the horse moving in all of its directions. So totally I have 8 coordinates which the horse can make with the possible positions on the chessboard. Is how we connect the coordinates with real life system. The possible coordinates are 8 coordinates which the horse makes with the Cartesian form. The first being 1 unit this thing, and then 1 unit, the first position being 2 units right and 1 unit this, and this being P2, and this being P3, and this being P4, and then P5, P6, P7 and P8 is the different types of positions which are made by the Cartesian system. Is how we understand the connection of the movement of horse with chessboard. There are 8 different positions made by the horse in the chessboard when we locate through the Cartesian plane in XY coordinate system. Now let's see how we can plot the points on the coordinate system accurately using the graph scale. What is the scale? Before we try to understand the Cartesian plane and locating the points in the Cartesian plane, the scale is the base which gives us approximation in locating the points. Let's see in brief about the scale used in plotting the points. Let's see what a scale is. Imagine I take an x-axis and a y-axis with origin, with xx dash being the x-axis and yy dash being the y-axis. Now scale is the measurement used when we move the points along x and y-axis. For example, when I move with a scale, when I locate with points 1, 2, 3, 4, etc., I mean that I have measured this to be 1 unit, and on the graph paper the grid lines are generally at a distance of 1 centimeter each, and that grids are taken as the base of the scale. That is, for every grid which is generally denoted by the scale for x-axis is 1 centimeter equals 1 unit if this is taken to be 1 unit each, and y-axis if I take 1 centimeter to be 1 unit, then in this case I refer to this distance of 1 centimeter on the graph sheet grids to be 1 unit what I identify. Similarly, on the left side, I take every 1 centimeter of the grid on graph paper as 1 unit, so every unit refers to this. Because I also refer my y-axis with 1 centimeter equals 1 unit, I have this to be 1, 2, 3, 4 and 5, and this would be -1, -2, -3, -4 and so on and so forth. So I have each of the coordinates plotted on the scale of x and y axis. Is how we plot the scale. Scale is very essential when we plot on the graph sheet, because scale gives the accurate measurement of the point from its initial position 0. Let's see another example through which we can understand the scale more better. Now that we have discussed about scale in the previous session, let's try to take another example problem to understand the concept more better on scale used in plotting the points. For example, I have an example problem which says plot the point 1, 2, using the scale, one centimeter equals 1 unit on y-axis and 1 centimeter equals 0.5 unit on x-axis. Now let's try to understand the scaling concept better using this example problem. The example problem reads clearly, plot the point 1, 2 using the scale. That means the scale is clearly referred out here with suitable distance fixed. Now the scale in this problem says 1 centimeter is 1 unit which we need to take on y-axis, and every 1 centimeter of the grid in the graph sheet should be measured with 0.5 units on x-axis. So let's see how we understand the scale concept practically on the graph sheet. Now that I have the point, let me just take the xy coordinate system, x dash, y dash. Now here my point refers to 1 centimeter is 1 unit on y-axis. Initially I start with x-axis, which says that every 1 centimeter of the grid on the graph sheet must be taken as 0.5 units. So here I have my origin, and these are the grids separated on the graph sheet. Now these 1 centimeter grids separated on the graph sheet are referred to be taken as 0.5 units on x-axis, as clearly referred in the problem. Therefore, I do not take this as 1, but I take this to be 0.5 units. Indirectly, the 1 centimeter measurement on the graph sheet by this grid refers to 0.5 units actually by the scale, is how we understand the scaling concept. Similarly, the distance from here to here must be 0.5. Therefore, the next value would be 1, because 1 minus 0.5 would give me 0.5, or 0.5 is added further. You can also refer this as 0.5 added to this refers to 1. So when I want to find the next coordinate, it is about adding 0.5 to the previous value of 1, which gives me 1.5. The next is adding 0.5 to the previous, which is 1.5, which gives me 2. And then on the left, minus 0.5, minus 1, minus 1.5, and minus 2, etc. This is how the scaling is done on x-axis according to the given question. Next comes the scaling on y-axis. How do we scale on y-axis? Clearly on y-axis, the measurement refers 1 centimeter to be taken as 1 unit. So every 1 centimeter of the grid is taken to be 1 unit. So I get this to be 1, 2, 3, 4, 5. And every unit down is referred as minus 1, minus 2, minus 3, minus 4, etc. is how we get the different grids out here. So scaling on x-axis is done with 1 centimeter equals 0.5 units, and scaling on y-axis is done with 1 centimeter equal to 1 unit. And then comes the locating of the point on the Cartesian plane, this Cartesian plane. So let's see how we can locate the point on this respective scaled coordinate plane. Clearly I see the point here. Let me denote with 1, 2. Now here this refers to the x coordinate being 2, 1, and my y coordinate being 2. So let's see how I can locate with x equals 1 and y equal 2. So as I see the x coordinates moving horizontally along the right and left, and the y coordinates moving vertically up and down, so clearly the x coordinate moves 1 unit to the right. This being positive, it moves 1 unit right, and then it moves 2 units up. So I get the point to be here, which is 1 unit and 2 units to this, and therefore I get the point P, which is exactly out here. So this is my point 1, 2, depending on the scale as given respectively for x and y axis. So my point is 1, 2 is how we get it. It's easy. Plotting the point is based on scaling the plotting and then locating the point respectively through that scale. Now that we have discussed about scaling concept, the rules of scaling the x and y axis, let's see now how we can locate the points and how are the steps and procedures involved in locating the points in the Cartesian plane, respectively through the given scales. So let's take an example problem to understand the concept. Plotting the points is the session for today. So let's see about plotting the points. So for example, I have a question which says, plot the points P is plus or minus 1 and plus or minus 2, and Q is plus or minus 2 and plus or minus 1 on the Cartesian plane. So I would like to plot the points P and Q in the Cartesian plane, provided that the given condition is with a scale 1 centimeter equals 0.5 units on each of the axis. On each of the axis is what is the given question. So let's see how we can do this problem through the scaling concept and locating the points exactly on the graph sheet. Now that it's given clearly with the scale that 1 centimeter is 0.5 units on both x and y axis, we take the centimeter of 1 centimeter of the grid to be subdivided with each of the unit being 0.5 unit difference. So let's see how we can make the scale before we locate the points P and Q. Considering the Cartesian plane x, x dash, and y, y dash, let's try to make the 1 centimeter grids. The first thing we identify in doing this type of problems is locating the grids. So I just mark the grids, each of them, and then here each of them is 1 centimeter, and then here. Now that on x axis, on each of the axes, in the sense both on x and y axis, the scale is the same, is what the question refers. So on x axis, starting initially with x axis, my 1 centimeter is 0.5 units, and therefore this moves each of 0.5, 1, 1.5, 2, 2.5, etc., as in the previous problem. Similarly, on the left, it moves minus 0.5, minus 1, minus 1.5, minus 2, and etc., with minus 2.5. Similarly, on y-axis, it is 0.5, 1, 1.5, and 2, minus 0.5, minus 1, minus 1.5, and minus 2 is how I divide the scale with 1 centimeter equal to 0.5 units. Next, it's now about plotting the points on this scale for P and Q. As I observe, there are different values for P and Q, so in this case, plotting the points is very easy if you can convert the given points into the tabular form. So let's see how we can do the plotting concept through the tabular form. As seen here, I clearly see that there are P and Q points out here, which I take it in the form of the table. I make a table of x and y values where this is x and this is y. Now let me pick all the x values of both the points P and Q. So I have first x equals plus 1 and then x equals minus 1 is what we get. And again I have for P, these are the coordinates for P, and then I have x equals to 1 and x equal to minus 1 for the coordinates of Q. So each of the coordinates have x as plus or minus 1 and plus or minus 2 is what we get. Then I have my P equals 1 implies P equals 2. And P equals minus 1, x equals minus 1 implies y equals minus 2 is how I understand this problem. Therefore, 2, 1 and minus 2 minus 1 is what we get as the coordinates plotted on x-axis. I take the plus or minus respectively for plus and minus. And therefore, I get 4 different coordinates for each of P and Q. So I get the point 1, which is 1, 2, then minus 1, minus 2, then 2, minus 2, and minus 2, minus 1. So on the whole, I have 4 coordinates which I'm going to locate on the coordinate system. First, coming with this, I have this to be 1, 2. So 1, 2 is my first coordinate. So in this particular problem with this tabular form, we're going to plot the points each of 1, 2. Initially, my first point is 1, 2, where x is 1 and this, which is 2. And then coming to the second point, I have my x, which is minus 1, and y, which is minus 2, which comes out here. Similarly, my third point, which is 2 minus 2, is 2 and minus 2, which comes out here. 2 units right and minus 2 down. And my fourth point, which is minus 2 minus 1, moves minus 2 left and minus 1 down, is how I locate the 4 points, this being 1, 2, this being minus 1, minus 2, and this point being minus 2, minus 1, and this point being 2, minus 2. One, 2, minus 1, minus 2, 2, 1. This is 2, 1 and 2, minus 2, minus 1. So my third coordinate, which is 2, 1, is out here, but not 2, minus 2. So I have the coordinates minus 2, minus 1, minus 1, minus 2, 1, 2 and 2, 1. The four coordinates denoted by P and Q, represented or plotted on this Cartesian plane using the scale 1 centimeter equals 0.5 units and 1 centimeter equals 0.5 units on both x and y axis. Plotting the points is done through the construction of the table with the first row with all x values of the given points and the second row with all the y values of the given points, and then plotted accordingly through the pairs. The first pair gives the first point, the second pair gives the second point, the third pair gives the third point, and then the fourth pair, which gives me the fourth point on the Cartesian plane. Is how we understand the construction of or the plotting of the points on the Cartesian plane using the concept of the scaling process. Scaling and plotting the points on the Cartesian plane. Now that we have discussed about the Cartesian plane and the plotting of the points on the Cartesian plane with its respective definitions, let's now define or discuss about how we can just identify the points on the Cartesian plane, or how we can identify the coordinates of the points in the Cartesian plane if the point is given in the Cartesian plane. It's just like the reverse process of what we have learned in the previous sessions. Given the point in the Cartesian plane, what are its coordinates is what we are going to investigate in the session. Let's see, for example, to start with the heading, reverse process. Given the point in Cartesian plane implies, how do we identify its coordinates is what is called the reverse process, because in all the sessions we have discussed about a point which is plotted on the Cartesian plane. But what if the point is given in the Cartesian plane and we would like to locate the point with its coordinates? The values of its abscissa and ordinate is what we need to discuss in the session. Reverse process is equally important as the forward process of learning to make the learning more stronger. So let's see how we can understand the concept more stronger and more deeper using this reverse process of understanding. For example, I have a question which says find P in the plane. Say for example, I have the given plane which is x-axis, y-axis. This is etc. And on the left I have minus 0.5, minus 1, and minus 2, etc. And then I have this to be and here I have clearly that this is the x-axis and this is the y-axis, and the scale on x-axis is 1 centimeter equals 0.5 units, and the scale on y-axis is every 1 centimeter grid is 2 centimeters, is 2 units. So I have the scale for this problem, which is on x-axis 1 centimeter is 0.5 units, and on y-axis 1 centimeter is 2 units. Is how we understand the scale on x-axis and y-axis. So coming to the problem, if I have a point, say located out here, and I have another point, say it's out here. Let's see how we can locate these points P and Q using the reverse process of understanding the concept. Now that the point is given without its coordinates, the challenge is to find the x and y coordinates, that is indirectly to find how many units the given point is moving from its initial position, either right or left or up or down. Is how we understand the concept of identifying the point. So let's see how we can do that. Here is point P, which clearly is understood to start from initial position, moving 1, 2, 3. So it moves 1.5 units to the right as given by the scale of 1 centimeter 0.5 units. So it moves 1.5 units to the right, and then this point moves from here back 1, 2, 3. So I understand that the point P is obtained from moving 3 units, 1.5 units to the right and minus 6 units down, and therefore the coordinates of P are nothing but minus, moving to the right is positive 1.5 and moving to the down is about moving 6 units, that is minus 6 out in the y coordinate. Therefore, I have my coordinates of P, which are 1.5 and minus 6. Is how I understand the locating of this point with its x and y coordinates. Therefore, with the concept of locating the position of P with respect to its initial position, moving right and then down, or moving left and then down, etc., we can locate the coordinates. In this case being moving 1.5 units to the right, x coordinate is this, and minus 6 is the y coordinate. Therefore, for this P, my abscissa is 1.5 and my ordinate is minus 6. Similarly, let's see the coordinates of Q. When I have the coordinates of Q, I clearly see that this is the point which moves minus 1.5 units left. Q moves 1.5 units to the left and then moves 1, 2, 3. So I have this exactly between 4 and 6. So I assume this to be 5. So Q moves 5 units up. So Q moves minus 1.5 units, 1.5 units to the left and then 5 units up. Therefore, I have this to be my coordinates of P, Q, negative 1.5 and 5 is how I locate the coordinates of Q and P. P is 1.5, minus 6 and Q is minus 1.5, 5. Locating the point from its plotted point. Locating the coordinates of P using the reverse process of understanding the graph is what is the session. Next comes that we have discussed about Cartesian plane, locating a point, and the reverse process of understanding the finding of coordinates using the point located or plotted on the graph. Next comes in applying this into the real life situations. So let's take the opening problem which we have discussed about a ship in the sea and reaching the bank, reaching its destination. So when the ship would like to reach to the seashore, let's see how it can estimate through the use of coordinates. For example, I take the sea. Now here is the sea in which there are small islands. So here is one island and here is another island. And then here is one. So this is island 1, this is island 2, island 3 is how we understand the concept. Now the ship which is out here would like to reach to the shore. So let's see where it reaches. Now the person in the ship would be puzzled to know which is the nearest island to which he can reach. So let's see this interesting problem connected with coordinate system. He can resolve the issue by just using the coordinate system or the Cartesian plane. So this person is wondering about moving to the nearest island. So how does he estimate moving to the nearest island for the seashore? So let's see how that can be done. A person estimates that this island is, say, the person in the ship estimates that the island 1 is two units to the right and 3 units to the top is how the person estimates the ship from the island 1. He also estimates that the island 2, which is just besides this on the other side of the ship, is estimated to be 3 units to the left and 4 units up. So this ship moving to island 2 must move 3 units left and 4 units up. And the third island is about the person moving to the island 3, where he is 5 units left and then he is 2 units down, is how he estimates each of I1, I2 and I3. I1 stands for island 1, I2 stands for island 2 and I3 for island 3. Now he is in this dilemma. He needs to solve this puzzle of reaching to the nearest island. So he is puzzled between island 1 and he is puzzled between island 2 and he is puzzled between island 3. Which island does he reach? Is the biggest question. He needs to search for a mathematical solution for this problem. Imagine that he is first reaching to the destination of island 1. So let's see how he can just do that. As I see this, I clearly see that Let me take the scale of 1 centimeter as 2 units. And let me locate the first point which the ship can reach to island 1. Now for reaching island 1, the ship has to move 2 units right and 3 units up. So here is where the destination is of the ship. Towards island 1. This is island 1. And next, the next destination is about reaching island 2, where the ship moves. Here is the ship. Where the ship has to move 3 units left and 4 units up. So it has to move 3 units left and 4 units up. So here comes the island 2 into this place. And then the ship has to move from its initial position origin to reach island 3 for a distance of 5 units left and 2 units down. So 5 units left and 2 units down is about moving to this place I3. So I have my destination, which is island 3, island 2 and island 1. So once I reach to these 3 lands, I get that there are 3 positions which the ship makes. And the question comes on how we can just find the nearest distance that the ship moves to reach to the islands. So let's see what is the least distance made by the ship to reach to each of the islands. Now as we see here, this is clearly origin and this is I1, I2 and I3. Let me first locate the coordinates of I1. So let's see how we can locate each of the coordinates I1, I2 and I3, and then come to the actual puzzle of solving the nearest distance which the ship can reach to the island. Which island would be the nearest to the ship? Now let's see the distances of the ship from each of the islands I1, I2 and I3. Before that, we need to locate the coordinates of I1, I2 and I3. So here I identify that the coordinates of I1 are 2 and 3. And the coordinates of I2 are -3 and 4, because it moves -3 left and 4 units up. And the coordinates of I3 are -5 to the left and 2 units down, so it's -5, -2. Therefore, the coordinates of I1 are 2, 3. The coordinates of I2 here are -3 and 4, and the coordinates of I3 is -5, -2 is what we get for each of the coordinates. Now let's also take the initial position of the ship into account, where the initial position of the ship is denoted by O, which is origin. Now comes the question on which island is the nearest to the ship in the sea. So in order to find the nearest distance, it's all about finding the distance of O from I, the distance of O from I2 and the distance of O from I3. Now once we know the distances, we can find the least distance, which gives the least. So let's see how we can use the distance. So let's first initially find the distance of the ship from island 1, which is from O to I1, and that is the distance of ship from island I1. So clearly we know that the distance of the ship from island I1 is OI1, and this can be found by using the distance formula between O and I1. So distance of O from I1 is root of x2 minus x1 whole square plus y2 minus y1 whole square. The formula for distance between 2 points. So the distance of O from island I1 is root 13 units. Similarly, my next target is to find the distance of the ship from island I2. Here being the island I2, this is the distance which I need to find. So distance of ship from island I2 can be found as OI2, because this is origin and this is I2, so OI2 refers to the distance from island I2. Using the same formula for distance, root of x2 minus x1 whole square plus y2 minus y1 whole square, I get the distance from O to I2 using the coordinates of I2 minus 3, 4 and origin which is 0, 0. Therefore, I have this to be minus 3 minus 0 whole square and 4 minus 0 whole square. And this, on further simplification, gives minus 3 whole square, which is 9, and 4 square, which is 16, which gives me root 25, and which is 5 units. So distance of ship from island I2 is 5 units. Similarly, the distance of ship from island I3. So how do we find the distance of ship from I3? It is the same repetitive process where the distance of O from I3 is OI3, and which is using the distance formula, and there I get the distance from O to I3, which is root of minus 5 minus 0 whole square plus minus 2 minus 0 whole square, which is root of 25 plus 4. 5 square, which is 25, and minus 2 whole square, which is 4. So 25 plus 4, which is root 29. So clearly I get this to be root 29 units. Therefore, by verifying through the 3 different distances, I find that distance of the ship from island I1 is root 13 units, distance of the ship from island I2 is 5 units, and distance of the ship from island I3 is root 29 units. So as I see clearly out here that root 29 is greater than root 25 greater than root 13, I clearly see that this root 29, which refers to island I3, root 25, which refers to island I2, and root 13, which refers to island I1, makes me clearly understand that island I3 is the farthest from the ship and island I2 is the next farthest from the ship, and the island I1 is the nearest from the ship, and therefore the person who is sailing in the sea in the ship would definitely reach to the target of reaching island 1 because it is the nearest and easy to reach for the safer side. Hence, the person has resolved the process of reaching the destination of the puzzle of 3 islands by using the concept of coordinate geometry. In this case, I am in the ship, I reach island 1 because it is the nearest of all the 3 islands. This is how I understand the applications of coordinate geometry and Cartesian plane in real life, resolving the issues through real life situations. Now that we have discussed about the coordinates and the x coordinate being called the abscissa and the y coordinate being called the ordinate, we have a specific terminology even for the point we refer on the Cartesian plane. Let's see how we can represent or use the terminology, the correct terminology for a coordinate in a Cartesian plane. As we have seen through the coordinates, here comes the importance of identifying the definition of ordered pair. As we all know that a pair is combination of 2 different objects taken together. Here the pair refers to x value and y value taken as a pair. So an ordered pair refers to the x and y coordinates or the abscissa and the ordinate taken in the bracket paired together. That is, when I take a point 2, 3, it indicates that for x equal to 2 is being paired with y equal to 3, and they are associated with each other. Every pair have a certain relation, and here the relation is that these 2 coordinates pair to form a point. So these 2 coordinates x and y are paired to form a point in the Cartesian plane. So here I have the Cartesian plane in which 1, 2, 3, 4. I clearly see my x coordinate, which is 2, and y coordinate, which is 3, are paired together to form a point 2, 3. The pair forms a point in the Cartesian plane. Is how we understand the pair. But what is an ordered pair? It is very important that when you take the coordinates x and y taken in the pair, reversed order will never be equal. An important note to be made in the branch of mathematics. The pair xy will never be equal to the pair yx because they maintain an order, and hence every point xy in the xy coordinate system or the Cartesian plane is called an ordered pair. The first value refers to the x coordinate and the second value refers to the y coordinate. Abscissa and ordinate are ordered, and xy cannot be equal to yx for all x and y belonging to R, is how I understand the properties of ordered pairs. The pair must be ordered. For example, 2, 3 point cannot be equal to 3, 2, which can clearly be verified because 2, 3 is here, and when I take 3, 2, I move 3 units right and 2 units down, and then I get this point to be Q. Therefore, my 3, 2 and 2, 3 are not exactly plotted at the same point. They are different from each other, which clearly proves that 2, 3 is not equal to 3, 2. Therefore, xy is not equal to yx. The 2 points are equal only when they are in order. Xy must be equal to xy, but xy cannot be equal to yx, is how I understand the definition of an ordered pair. An ordered pair and its properties. Let's see some properties connected with coordinates in the Cartesian plane. As we have discussed about the ordered pair in which x, y in a Cartesian plane can only be xy, but xy cannot be equal to yx. Say, for example, let me take the properties. If I take the ordered pair x, y as a point and I say this is equal to the Cartesian ordered pair when it's reversed, then in that case this is possible only when x equal to y. Is how we understand the property. This property can never be true if they are not equal. They have to be equal. If the abscissa and the ordinate are equal, only then I get the reversing property holding true. For example, let's take an example problem. If I have the property 3, minus 2, clearly when I reverse, we know that this when reversed gives me minus 2, 3. So the reversing of the point 3 minus 2 to minus 3 clearly makes me understand that 3 minus 2 is not equal to minus 2, 3. But if I take, say for example, another set of example which says 5, 5. I have the coordinate 5, 5 which I would like to reverse. So when I reverse the x and y coordinate, I get here again 5, 5. Therefore, in this case, my coordinate in which the coordinates are reversed are both equal. Therefore, in order that xy must be equal to yx, I should have the condition that this x and this y must be same. Xy equal to yx only when x is equal to y. If x is not equal to y, xy is not equal to yx. Is how we understand the properties connecting the Cartesian plane. Now that we have discussed about the coordinate geometry, now comes on how we can represent the axis in different forms in real life. As we have discussed about x and y axis, x axis being the horizontal axis and y axis being the vertical axis, what would be its significance in real life? Let's see an example problem to understand this concept more better. For example, I have axis representation in real life. X-axis and y-axis representation in real life. For example, I have a table of time and distance, where t stands for time and d stands for distance, time in seconds and distance in meters, is how we try to connect. Say for example, I take a real life problem of a 100-meter sprint race where the Olympic participants tried to run in 100 meters. Usain Bolt is what I'm talking about. So here, let's try to take the time and distance problem in understanding the axis representation in real life. For example, say in the first 2 seconds, the distance run by the Olympic sprinters in average is 30 meters, 20 meters, and then say the distance run in 4 seconds by the sprinters is 39 seconds, 39 meters, and say in the distance run in 7 seconds is 71 meters, and the distance run in 8th second and the distance run in 10th second is say 100 meters. So approximately I would like to say that this is the table of all the time and distance. The first row refers to the time taken by the sprint participant in each of the seconds, and the second row represents his running distance of 100-meter race. So this gives me a picture of a real life problem which I'm going to convert into axis representation. Quite interesting. So here the time refers to the first 2 seconds. The distance covered by the sprinter is 20 meters. Distance in meters, time in seconds. So the first 2 seconds, the distance covered by the sprinter is 20 meters. And for the first 4 seconds, the distance would be 39 meters as recorded, approximately. When the time taken is 7 seconds, it is assumed that the distance traveled by the sprinter is 71 seconds. For the 8th second, it is said to be 89 meters, and then coming to the 9th second, it is 94, and 10th second, it is 100. Is how I understand this in real life situation. How do you convert this into axis is the biggest question out here. In order to convert this into axis, we try to take always this is called t-axis because x-axis is now represented by the variable t. Your x is now the time in seconds and your y is now the distance in meters. So I have here the time which I'm going to denote with 2, 4, 6, 8, 10, 12. Now the scale. What am I going to do with the scale? As we have discussed that every graph has 1 centimeter grid distance, we just represent the 1 centimeter grid distance with different values as scale. So here, because my values are up to 100, taking each of the grid with 1 centimeter equal to 1 unit on y-axis becomes a tough challenge. Therefore, I increase the scale on y-axis. So each of the 1 centimeter grid is taken to be 25, 50, 75, 100, 125. So here I adjust the scale on x-axis, which is my t-axis, to be 1 centimeter equal to 2 units, and then on this d-axis, which refers to the y-axis, the distance axis is 1 centimeter equals 25 units. This makes me clearly understand that the scale is a significant tool in making the window setup so that I can understand how the different values can be adjusted through the scale. A scale is an important tool in adjusting the values into the graph. So here I have my t-axis which refers to the time and my d-axis which refers to the distance of the sprinter in 100-meter race. So my time is in seconds and my distance in meters for the 100-meter sprint race. So let's see how I can plot the points. I can have my t is 2, my distance is 20, approximately here. My t is 4, my distance is 39, approximately somewhere here. My t is 7, my distance is 71, so I have this to be approximately here. That's how I get. When I have 8 seconds reached, my distance would cover 18. I have this covered, and then 8 seconds is 89, which comes. And 9 seconds is 94. And 10 seconds is 100. Is how I make the distance time graph. This graph is called distance time or time distance graph, where this refers to t-axis and this refers to d-axis. So any problem in xy coordinate system can be applied in real life situation. For example, this being the time and distance of a 100-meter sprint participant in the Olympic Games. The chart of Usain Bolt.